Good day. In this lecture video, I'm going to discuss solution to sample problem 2 on lecture 4 about resistance. Okay? So the resistance of a cylindrical brass conductor 0.5 centimeter diameter and 3 meters long is 0.0108 ohm. For letter A, determine the resistance of a cylindrical conductor of same material and same temperature and having diameter of 0.25 centimeter and length of 8 meters. The letter B, what is the resistivity of brass in micro-ohm cm? Okay, so the first step is, of course, to determine the given and target variables. Okay, so by observing the problem, we are given two sets of dimensions. Okay, so we denote those sets as 1 and 2 respectively. So we have R1, D1, and L1. Then we're given another set of dimensions of the same material and same temperature, D2 and L2. Then for letter A, we're tasked to solve for R2. Okay. Then in letter B, uh, we're tasked to solve for the resistivity of brass in micro-ohm cm. Okay. So before substituting the formulas, so first we determine what are the relevant concepts that will be used and our general approach in solving this problem. So we'll use this formula, okay, the resistance, okay, as a function of the physical dimensions of a conductor. Okay, so this formula states that the resistance of a conductor is directly proportional to its length and inversely proportional to its cross-sectional area A. And also it is also a function of the resistivity, which is represented by the type of material of the conductor. And then the second formula, so we just rearrange the first formula because we'll be using this formula. Okay? And also take note the same material and same temperature. So this implies for the two sets of dimensions, the resistivity is constant. Okay? So with that, so let's execute our solution. So for letter A, okay, we equate the resistivity for the two sets of dimensions. So we have rho 1 equals rho 2. And then we substitute, okay, using this formula, we have R1 A1 over L1 equals R2 A2 over L2. Okay, so before substituting the values, okay, we express the unknown variable R2 in terms of or the symbolic expression of R2 in terms of the other variables. So simplifying, we have the following expression. Okay, so after some algebraic manipulations, and then we substitute the values for R1, A1, A2, L2, and L1. But take note, the cross-sectional area for both cases is given that we have a cylindrical brass conductor. So for a cylindrical brass conductor, the cross-sectional area will be a circle. Okay? And the formula for the area of a circle is, in terms of its diameter, is equal to A equals pi over 4 d squared. Okay, so we substitute that and we can now substitute the values. Okay, so take note, uh, before inputting these numerical values in your calculator, make sure that uh, the units are correct. Okay, so for example, so for this expression, take note that the cm squared will cancel out. Okay, and also for this term, okay, both meters will cancel out. So we expect the unit of R2 to be ohms. So we have ohms here. So we don't need further conversions to solve for R2. So solving for R2, we obtain a value of 0.1152 ohm. Okay. And for letter B, okay, rho is equal to RA over L. So as seen in this equation, okay, we can use either side of the equation. Okay, both will yield the same value of resistivity, but as a rule of thumb, okay, we use the left hand side. Okay, so why do we prefer the left hand side? Because the value of R1, L1, and D1 are given. Okay, so this in a way this gives us protection from error propagation. I mean, for example, uh, for some reason you obtain a wrong value of R2, whether during uh, some manipulations, or we forgot to convert, for example, one unit to the correct one, or you simply mistype some numbers in your calculator. If you use the right hand side R2 to solve for row 2, then you also expect if R2 is incorrect, then your answer letter V will also be incorrect. Okay? So as a general rule of thumb, try to solve the problems independently whenever possible. Okay? So row we have R1, A1 over L1, and then we substitute the values. And then again, we expect row to have a unit of micro ohm cm. Okay? So micro, that means times 10 raised to negative 6. So it has something to do with the order of magnitude. Okay? So we need ohm and cm on the numerator. Okay? So we have ohms here. Okay? Here we have the diameter as 0.5 cm squared. Okay? And then L1 turned out to be 3 meters as given. So in this case, we convert 3 meters to cm. So the conversion of 1 meter equals 100 centimeters. So instead of 3 meters, we have here 300 centimeters. And then we perform dimension analysis. So cm here will cancel out. Okay? So we have ohm times cm and whatever the magnitude of the answer. So in typing this to calculator, we have row of 7.0686 micro ohm cm. Okay? So before ending this lecture video, okay, so let's at least try to evaluate if our answers make sense. Okay? So for example, for letter A, we have R2 of 0.1152 ohm. And again, we're given two sets of dimensions. Okay, and we know conceptually using this formula that if you increase the value of L, okay, or you decrease the area or you decrease the diameter, both will cause the resistance to, okay, increase. Okay, like that. So comparing the dimensions, we have L1 or L2 is greater than L1, and at the same time D2 is less than D1, or A2 will be less than D1. So for both cases, we expect R2 to be greater than R1. Okay? So the process that I just performed, take note, it does not guarantee that we have the exact answer. It only tells us that our answer makes sense. Right? In other words, if R2 turned out to be smaller than R1 due to some errors in whether manipulations or uh, wrong calculator stroke, okay, or so for some other reasons, then you have to it will give you a signal that something's wrong with your calculation and you have to recheck. Okay, so this ends sample problem number 2.